Historically, wood mid-rise light frame residential buildings often featured relatively simple plan geometry, regular and not overly extensive exterior fenestration, and most important structurally, a relatively uniform distribution of shear walls of roughly equivalent stiffness. The code provisions relevant to this building type have implicitly assumed these features. Traditional analysis techniques utilizing flexible diaphragm assumptions and floor-by-floor shear wall stiffness distributions were and continue to be adequate to analyze regularly configured buildings of this type. So with respect to the code environment, in the Uniform Building Code, there was a long-standing reduced lateral force requirement for light frame buildings 3 stories or less in height braced by wood shear panels compared to other bearing wall buildings. The 1997 UBC carried this exception forward. UBC R value for this building type more than 3 stories resulted in higher seismic design forces in current code, but it's interesting to think about it differently. For the lower R equals 4.5 system, the designated structural system could be a mix of wood shear panels, stucco, and gypsum board. While these materials cannot be combined within a single wall, their permissible use under the same R value allowed combinations in different wall lines and within the same wall line. So apparently the major change was restricting the use of stucco and gypsum sheathed shear walls, particularly in combination with wood shear walls, while the accompanying change of lowering the seismic forces for taller buildings braced solely by wood shear panels may have not been fully intentional. So for these taller buildings, the implicit code assumptions regarding relatively simple plan geometry, regular and not overly extensive exterior fenestration, and most important structurally, a relatively uniform distribution of shear walls of roughly equivalent stiffness continues to be important. However, many of these buildings currently being constructed now do not possess relatively simple plan geometry, have extensive exterior fenestration, and irregular distribution of shear walls at some levels. These buildings are growing increasingly complex as architects attempt to increase density, optimize the amount of natural light each unit enjoys, and provide articulation at the exterior walls. Note the scale and plan configurations of these typical wood mid-rise light frame residential buildings. Here is a site plan of a typical current multi-unit residential project. Note the difference in plan geometry between the multi-story residential buildings and the retail buildings in the bottom left-hand corner. When the structural design of this building type commences, there are many decisions that have to be made which will affect the lateral design, but most importantly for this topic, it's where are the shear walls and to what extent do they conflict with plumbing walls or the mechanical systems. Note also how this building type is composed of many distinct structural elements that make them difficult to analyze accurately. So what are some of the challenges engineers face when designing buildings of this type? Of course, there's diaphragm behavior uncertainty. Should we use a flexible diaphragm analysis or rigid diaphragm analysis? Of course, the code requirements. What about drift? What about diaphragm deflection calculations necessary if the building is adjacent to an existing building or requires a seismic joint somewhere? So an implicit assumption, again, is the code, is that these buildings have uniformly distributed shear walls of approximately equivalent stiffness. However, for this building type, this assumption is often violated at the exterior and at the first floor. So here's a typical plan for this building type. Note that virtually all units only have one exterior wall. There's a perpetual negotiation at the exterior for reducing walls to maximize windows and the need for natural light versus lengthening walls for the vertical lateral force resisting system. So wood mid-rise light frame residential buildings typically consist of a series of individual residential units divided by corridor and party walls. These walls function as the building's primary shear walls due to their length and regularity as well as their lack of penetrations. Notice the building's exterior shear walls are much shorter and stagger out of plane. The building's diaphragm aspect ratio is typically very low, ranging from 0.2 to 0.3 in the longitudinal direction, and in the diaphragm and in the transverse direction. These low diaphragm ratios directly affect the diaphragm behavior. So again, here's the shear wall layout. So Although simple to execute, usually a flexible diaphragm analysis, you need to have lateral force resisting elements on all sides of the structure, and you're supposed to calculate drift at each line of resistance. So even if a diaphragm can be idealized as flexible per code, using a flexible design presents some concerns. It can underestimate the forces distributed to the corridor walls, can overestimate the forces distributed to the exterior walls, and it may result in under-design of the diaphragm.